Hello everyone and welcome to a new video. A while ago I did a video showing how I upgraded my filament dryer, and in that video I added a better temperature control, ability to monitor and control the dry box remotely, API to integrate with my home automation and my 3D printing system, and so on. And same as with all my other projects, I released it as open source open hardware so anyone can follow along and build their own. And at that time, both of my subscribers really liked the video and said that they can't wait for the part 2. Now, this video was a relatively long time ago, and while I originally planned on making this part 2 video much sooner, life got in the way and I'm sure you know how that goes. But hey, better late than never, right? And actually, in the meantime, a lot of you have posted some great comments and suggestions. First of all, thank you all for doing that. I really appreciate it. Like pointing out that not everybody already has the exact same filament dryer like I do, and that they might be starting from scratch. Also, a lot of people seem to like the idea of making a larger multi-spool version of the dry box. So in this video, I would like to show you the new design for the dry box version 2 and walk you through some minor differences between the two versions and some design decisions. Also, because in the previous video, a few of you asked for finished boards, this time I did end up making a few extra PCB kits for those of you that said you don't want to deal with ordering the PCBs, soldering components and all that stuff. Totally understandable, and I hope this helps. And finally, I would like to show you how to build a complete DIY dry box from scratch, especially since so many of you have asked for it and it's pretty easy and straightforward to do. And as I said, I am going to do it, but first I have to be honest with you for a moment. I think this last part is going to be a bit tricky for me to do, and probably not for the reason you might think. You see, since recently, my dear Prusa MK3 that has been with me for almost a decade and went through so many upgrades and customizations was taken away from me too soon by this heinous blob of death. And I know some of you will say that this could be easily fixed and that I could get a new extruder assembly and so on, but honestly, I don't think I will do this. So for the time being, my Prusa MK3 is retired, and at the moment of recording this, I'm temporarily without a 3D printer. Luckily, I still have access to a 3D printer, but it's not the one I own. Also, in the future, I might do something interesting with the remaining parts of the 3D printer. So let me know down in the comments what would you do with it. And who knows, maybe we make a cool project out of it. Now, going back to the dry box and why I'm mentioning this, in this video, we will build a new dry box from scratch and show all the bits and pieces that you will need. But again, I want to be honest with you and say it will probably be a while until I actually need to use a dry box. And I have no idea what kind of printer I will have then, or if I will even need an external dry box. Or maybe my printer comes with a full enclosure or built-in dry box, or I don't know. So while I was using this new PCB design for quite a while before I lost my printer, and it worked great for me, this might actually be the first video where I'm making something that I don't know how or if I will end up using. So this means that I'm making this video to show you how to make your dry box. And that this video is going to be more focused on hopefully helping you do that, rather than being along the lines of, hey, I made this thing, copy it step by step. And I think this might be a good idea anyway, because instead of trying to make a one-size-fits-all solution, we will focus on guiding you in making your ideal solution. Because there can be so many tiny variations, like for example, you might want a dry box for 1 spool or 4 spools or 16 spools, or you want to use a tiny 50mm fan or 140mm fan, or maybe need space for a ton of desiccant or not at all, and so on. You get the idea. And all of these variations can drive the enclosure design in different directions and make the dry box look totally different. But the key components that you need are going to be the same. And hopefully in this video we can explain them well enough so that you can take this solution and season to taste, so to speak, until you get your ideal dry box. You get the idea. Okay, with that said, there is just one more very important thing to say before we begin, and that is to give you a warning and a disclaimer. This video, along with the DIY kit, is a demonstration and learning project provided solely for educational purposes. It is not a certified or safety tested appliance and must not be used for commercial, residential, personal, or for any purpose other than education and demonstration. Make sure you're aware of the potential risks of using such device and make sure to stay safe. Okay, after that disclaimer, hopefully now you understand that this is not a toy and we'll take this very seriously. With that said, Let's get started. The first thing that we will need is the heating element. Our dry box is designed to drive a 12-volt polymid heater that is 60 watts or less. These polymid heaters are used in many different applications and pretty much in every industry. But for us, this means that they are commonly available, very affordable, and come in all kinds of sizes and power ratings, which is perfect for an open source project. Now, I mentioned earlier, heater selection is one of those design decisions that would impact the design of the enclosure, or maybe the other way around, as in your enclosure size will drive how big your heater can be. For example, if you have a single spool enclosure, then your heater can be relatively small and does not need to have that much power. Also, I know it can be very tempting to go for the most powerful heater you can get into the box, because why not, right? But hear me out for a second. The heater is going to affect how much the dry box warms up, but when drying our filament, that is probably one of the less important things. Because let's say that we are going to dry the filament for at least 6 or 8 hours. And if our dry box reaches the target temperature in 5 minutes or 15 minutes, it does not really make a huge difference in the grand scheme of things because we still have 6 or 8 hours to go, so the difference is pretty negligible. Again, it's up to you, but I'm pretty sure you don't really need a 60-watt heater for a single spool dry box. Just for reference, this old dry box that I modified a long time ago had a roughly 7 or 8 watt heater and it worked fine. I modified it because I wanted better controls and some additional quality of life features, but I kept the original 7 watt heater and it worked great. Next, we need a temperature sensor for our heater. Compared to the previous version of the dry box, we are now using NTC thermistor as the temperature sensor. And same as last time, the temperature sensor will be attached directly to the heater, and this is how we measure the heater temperature. The reason for switching to these NTC thermistors is that they are much smaller, more common, and easier to source, and come in multiple different form factors. Just to give you an example, here I have 3 common versions of the otherwise identical NTC thermistor, but keep in mind that there are more versions available out there. Also, I don't know if there are standardized names for each version of these, so if you do, please let me know down in the comments. This one is probably the most common one. It's relatively small and has the NTC thermistor encased inside an epoxy. You just have to make sure that the epoxy part is in contact with the thing whose temperature you want to measure, which in our case is the heater. And that's pretty much it. Keep in mind that because they usually make these by dipping the thermistor inside an epoxy and then let it cure, the shape and size of the epoxy blob may vary. For our design, this is not important, but if you want to use it for something else, it's good to keep that in mind. Another common version is this one, where the thermistor is encased inside a metal cylinder. Compared to the previous version that might have some variation between those epoxy blobs, this one should always have the same diameter of this cylinder, which is nice if you plan on having something grab onto this cylinder or have it inserted into a hole or some other way of attaching it. But otherwise, they will work exactly the same. And then the third version that I have is this one, which has the thermistor encased inside an epoxy-filled metal cylinder. But compared to the previous version, it also has this small tab with a round opening for a fastener. So obviously this is ideal if you want to use a fastener to attach your sensor. For my dry box, I will use this first version, which is just the sensor encased in an epoxy, and then this gets inserted between the heater and the metal radiator. We'll show this later, but you can pick whichever version works best for you and allows you to securely mount the thermistor to the heater. Then we will need a temperature and humidity sensor for the inside of the dry box. This sensor will give us information about air temperature and air humidity inside our dry box, and based on that information we can decide what we want to do. And for this we are going to use SHC30 temperature and humidity sensor. Again, this is a very common and easy to source sensor, and there are many different versions and form factors available for it. In the DIY kit, the sensor will have this form factor, where the sensor comes inside a plastic enclosure that should allow you to either attach the sensor with a fastener or a double-sided tape. But same as with everything else in this build, there are many different versions available, so feel free to pick whichever form factor works best for your use case and your enclosure. We also want to be able to circulate the air inside our enclosure or maybe exhaust air out of it. For this, we are going to use a PWM fan. And compared to the previous version, Drybox V2 can now drive both 5V and 12V fans. And this allows us to have a lot more choices when it comes to fan power and also fan form factor. For example, now we can easily drive this tiny 40mm 5V fan, for example if your dry box is small or maybe not that wide, but at the same time we could also easily go for this 120mm 12V fan in case you need more airflow. Just make sure that on the PCB you put the jumper into correct position depending if you're using 5V or 12V fan, and you should be good to go. Again, same as with everything else, we have options and you can pick whichever one works best for you. Okay, now comes the hardest part, at least for me, which is making the enclosure. Because there are so many variations that this enclosure could have, and in order to make this video as helpful as I can, I made not one, not two, but 2.5 fully functional dry boxes. And as I mentioned in the beginning of the video, I will most likely never get to use these. Wait, what? Okay, never mind that. Just one more thing before we dive into making these enclosures. Since I mentioned that I don't know how or even if I will ever end up using these, the enclosure building part will be more focused on the general idea and what you could do, instead of being a step-by-step guide. But now let's take a look at the first enclosure, which is the single filament dry box. For this, I will use this 5-liter Rubbermaid plastic enclosure that is designed for kitchen pantry. I guess normally people hold their cereal or flour in these, but I'm going to turn it into a dry box and keep my spool of filament dry. Again, there is absolutely nothing in the design that requires you to use this exact same enclosure. You can use whichever one you want or have available. The reason I'm using this one is because I have it available. And keep in mind that whichever enclosure you end up choosing, you're going to have to make a couple of modifications to it. Again, don't follow my steps blindly, but instead consider what makes sense for your use case and what you have available. Inside this enclosure, I plan on housing the heater and the heater temperature sensor at the bottom of the enclosure, but obviously it cannot be in direct contact with the enclosure, otherwise it will melt the plastic. I also want to put the fan in the bottom side of the enclosure, and then the temperature and humidity sensor on the same side, because I plan on housing the dry box PCBA on the outside, and I would like to have all the cables coming out on the same side and maybe even through the same hole. Then in the middle of the enclosure, I will have a mounting feature that allows you to hold the filament and also allow it to rotate freely and keep it away from the heater. And finally, on the opposite end, I want to have a PTFE tube and a coupler so that I can easily feed my filament outside and out to the printer while it's still being in the dry box. Okay, now that we have a rough idea, let's build it. As I said, we cannot have the heater directly in contact with the enclosure because it could deform or melt the enclosure, or even worse, catch fire, and nobody wants that. So I took a thin piece of sheet metal, I believe this one is 0.4mm, and this should be stiff enough to hold our heater firmly inside the enclosure, but at the same time it should be very easy to cut into whatever shape you need. We can measure how much space we need and then add some extra for the standoffs. Then I used sheet metal cutting scissors to cut it to size. It didn't really turn out great, but you could also use a Dremel or some other tool to cut it into shape you need. It is not necessary, but after cutting the metal, I did sand the edges a bit to make them less rough and nicer to handle. Then I drilled the holes and attached 4 standoffs in each corner. This will help keep our heater spaced away from the enclosure. And later on, we can also attach fasteners through the bottom of the enclosure to make sure it's securely installed and doesn't move around. I also ended up painting this black just to make it look nicer, but you absolutely don't have to do this. At this point, we can also install the heater and the heater sensor onto this piece of metal. The Polymid heater has a double-sided tape on its back. You can just peel it off and stick it to this metal piece that we just made. Don't forget to sandwich the NTC thermistor in between these two. This ensures we have accurate temperature reading. And now we have our heater module that is good to go. Next, we need to prepare the fan so it can go inside the enclosure. For this, same as last time, I'm going to use the same Noctua 40mm PWM fan, I know that these are not the cheapest ones, but I like them and I think they're good quality. Also, I'm using this one because I have plenty of them laying around. So again, use whichever one you have available and that best fits your use case, budget and enclosure. For this fan, I have designed this very simple mount that will hold the fan at 45 degrees. This should help with circulating the air inside the enclosure and making the air temperature inside more even. Honestly, for this small of an enclosure, I don't know if this even makes any significant difference, but I don't think it hurts to have it, so I'm keeping it. I'm going to attach this 3D printed piece to the fan using these self-tapping screws that came with the fan. And on the other side, there is a spot for holding two M3 nuts. We are going to use these later on to install this module inside the enclosure. But for now, this module is also complete and good to go. Then the last part that we need is to build a spool holder. This will hold our filament spool inside the dry box and make sure it's able to spin while in use. Again, you have plenty of options, but for this build I have 3D printed a small cylinder and also added two bearings on each end. Then inside the enclosure we are going to mount two of these brackets to the wall and our 3D printed cylinder will fit right into these. And that's pretty much it. We have all of our modules ready for assembly. Now we just have to modify this enclosure by drilling a couple of holes. We can mark roughly where we should have mounting holes and then use a proper drill bit and drill to make holes. After that, it's just a matter of installing everything inside the dry box, connecting the wires to the dry box PCBA, and that's pretty much it. Our dry box is good to go. As a side note, just for fun, I did add some O-rings to each M3 screw, but I don't actually think those are necessary and may even be an overkill. But I just thought they might help with further sealing the enclosure and making it airtight. Okay, Sasha from the future here, and I had a couple of weeks to play around with this dry box and see how it works. Overall, I can say that I'm pretty happy with it, especially since this plastic enclosure is relatively thin and definitely not designed to hold heat inside. But it can still easily reach 45 to 50 degrees just with this 15-20 watt heater inside. And while we have a lot of room to put a more powerful heater inside, I think if you need temperatures above 50 degrees, it's probably better to get an enclosure with a thicker plastic or one that is better insulated. But given that this enclosure is very cheap, I think it was a couple of dollars, I'm pleasantly surprised by how well it performed. So if you decide to build one for yourself, consider spending some time and finding a sealed enclosure that has thicker plastic and is designed to hold hot stuff inside. This will have a lot more impact than getting a more powerful heater inside. Also, if you are drilling holes for screws or to feed cables through, consider how you're going to seal those to prevent heat from escaping. Over here I have simply used aluminum tape, but you can get more creative if you like. Also, for your standoff, screws and nuts, consider using nylon or PEEK parts if you can. It's not necessary, but they will conduct less heat than metal parts, and this will help you reduce overall amount of heat you are letting out of your enclosure. Or alternatively, you could 3D print an insert that goes inside the enclosure and holds everything together, and you don't have to drill this many holes. But other than that, I'm pretty happy with how this one turned out, and I hope that you now have a better idea on what you need to build your own dry box. As I said at the beginning of the video, my goal is to enable you to build your ideal dry box instead of following my steps blindly and hoping that we have the same definition of what is good dry box. Initially, my plan was to make a single video where I show you how to build the single spool dry box, the large multi-spool dry box, and another bonus version. Also go over the new electronics, how the UI works, the PID tuning, and few other things. But this video is already too long, and instead of rushing it or making the video even longer, I have decided to split this project into multiple smaller videos that are maybe a bit slower paced but easier to follow. So in the next video we will make a much bigger multi-spool dry box, so if you made it this far you might as well hit subscribe so you don't miss when that video comes out. Also hit like if you like this video or let me know your thoughts down in the comments. But otherwise, that's all for today's video. Thank you all for watching. My name is Sasha, and I will see you in the next one. Bye!